the next important component, which is going to be your gradients. Remember, you have the permanent magnet, your B naught. Gradients are important. Where did we see in the block diagram? If you remember, gradients we need for a purpose of changing the magnetic field in X, Y, and Z direction. How are they doing it? So you are going to have gradient coils, and of course you are going to have three different directions. Therefore, you are going to have X gradient coils, Y gradient coils, Z gradient coils, and you can see that all of them can be nicely put together, right? All the gradient coils can be assembled together, and you will notice that the name here given is X and Y are called saddle coils. Just to remember, why when you say saddle, what is saddle? Because otherwise X, Y, Z is three dimensions. How do you remember everything? What do you mean by saddle? I think if you look at, in this example, if you look at Y gradient, you can vividly tell why the saddle, horseback. So if you look at this, you can clearly see why the name is given as saddle. It looks like saddle. So immediately you can recognize, oh, it is on the curvature surface. Y is in one direction, the other is also in X. Both of them will look like a saddle. That's why it's called saddle coil. So Z therefore will be your two parallel circles here, right? Z is your opposing coils. Notice how we described going forward along the bore where the patient will go from his head to feet. That is our Z direction. So this is kind of your bore. This is your Z direction. So your coils are in perpendicular to that. I found a better animation here, right? More well done 3D with color. So this is the patient. This is my Z axis, right? Patient lying axis. So this is how the coils are arranged. Z coil is perpendicular to the patient axis. So that is your Z axis, and then the Z coil, and then your surface saddle coil or your X coil and Y coil are arranged here. Okay, so let's see now. What important component is gradient? What does that do? What does this gradient do? Notice its role is to excite selected volumes with select frequency. In other words, we want this magnetic field strength B, right? Static field. We need that to change as a function, as a function of position, right? Different locations should have different field. That is what this tries to accomplish. How does this try to accomplish? What are the components? What are the parameters of interest when you talk about gradients? Components are, obviously you have to have a coil, right? So components are gradient amplifiers and gradient coil. So you have to have amplification and you have to have the coil. Parameters are also very straightforward. Jargon is slightly specific to this. But what is gradient? I mean, we know this from mathematics. What is gradient? It is just changes. When we talk about anything that is changing, that means you are interested in the slope. Slope tells us how fast it changes or how slow it changes, right? So slope is, so your gradient is nothing but something to do with rate of change. So gradient here, what is it that we are changing? The field strength is what we are changing. So parameter is gradient strength. So its units has to be magnetic field strength. So it can be either Gauss or in Tesla. So it is in 1 to 6 Gauss or 10 to 60 millitesla. But change over length. So either in centimeters or in SI it is MI. In meters. So you have parameters is gradient strength. How does gradients, the magnetic field strength, how fast or how slow it changes with length is one parameter. Clearly we are talking about how fast it changes. You turn on, how fast does it change, right? So there somewhere time should come in. That is called as your slew rate. Your change 5 to 250 millitesla per meter per millisecond. How fast this gradient changes. Apart from that, obviously something changes. The parameter of interest is the length over it is changes, because then that will determine absolute terms how much is the field strength at different endpoints, right? And homogeneous volume over which you can pretend that that particular field strength is homogeneous. So all these are important parameters. So your coil essentially is changed here. B is always in Z direction, right? We are always interested in the Z direction, but it is slightly changed based on the slightly changed based on the gradient properties. So Gxx, gradient strength, Gx, Gy, Gz. So this is your B in the Z direction. Notice now the Z direction is, I mean, I always use this, but now patient is lying, so it is always head, foot to head, that direction. Of course, you have some limits at which you want to keep the switching. You cannot change rapidly because you are human body, right? You don't want to get into unknown trouble of switching its properties so rapidly. So there are some limits. Okay, let's get into some details. Of course, so the advantage of having these gradient coil is you can having these limits, right? More, the better it is. Increase the imaging speed, so you can capture faster changes. So there are advantages. You want this to be as high as possible, but there are limits, right? So it will enable you to do fast switching, but you have to operate within limits. So let's look into the detail. If you take Z gradient, so notice is a very nice sketch. So this is your Z, right? Patient lying. So the coil is perpendicular, right? So this is your two loops that you have. So notice what happens if I pass a current I in clockwise direction here and I in anti-clockwise direction, you are going to have opposite polarity. Okay, and depending on the length of separation and the diameter of this, your field strength B of Z can change. See, so essentially from head to toe, you are going to have different experience, different field strengths. That is what this is saying, right? So by changing the Z gradient or the Z coil, enable us to change the field strength in the Z direction. To put it into the coordinates here, X, Y, Z, right? Now Z is along the patient, so this is how we are going to do. So the B is always, your B naught is always in the Z direction. The Z coil essentially gives this gradient GC, right? How it changes here. So it is changing the B naught experienced as a function of length in Z direction. So naturally you would expect similar thing for X and Y. Notice there is a typo here. This has to be a X gradient. So the two other things have their radius, right? The coil radius and the length over which the coil is there. So those are your parameters. And you can see how what is the effect of gradient, right? The length of this arrow is changing. The length, any vector, what you see, length is a magnitude. So the field is changing. Of course, it comes to 0. So it's positive, negative, high, becoming 0, increasing, but along X direction. If you use X gradient, if you use Y coil, Y gradient, the gradient changes in Y direction. All the time, notice our B naught is in this direction, in the Z direction. These are small changes or the gradients along each other. This is what the XY gradient coil accomplishes. So what are the specifications that we typically get? Oh, you can change 1 to 6 Gaussian per centimeter. Switching times are very, a fraction of millisecond. Recall from our physics, what we were going after, T1, T2, right? A short TE, but all of those were still in the tens of milliseconds. So here you are looking at fraction of millisecond switching time. So it is likewise your slew rate. Only millitesla per minute per millisecond. Right? So you have enough cushion. So everything is operating within the limit. Whatever you do here, it has to be within the known approved legal limits. Okay. So move on to gradients are done. The other most important things are RF coil. Like I said, RF coil, why do you need the RF coil? Remember the B1, right? The B1 to push the magnetic field around. So you need that. How do we do that? First is on, like the alpha pulse, 180 pulse that we talked about. That is excitation pulse. So that is on the transmission mode. So you can have a RF coil for transmission mode. You can have transverse component that are cutting, right? XY component. So you can have another coil. So this is transmission mode. This is only receive only mode. So technically you have broadly you have three different categories. You can have transmit and receive coils. You can have receive only coils. You can have transmit only coils. Okay. What are these coils? These are essentially, see, how we are talking about is, this is all free induction. There is a frequency and you are measuring the frequency. So that means you know the frequency, you are tuning in to a frequency. So essentially this coil and its circuits are nothing but a resonant circuit which is tailored, right? Tuned with capacitors for efficient transmitting and receiving at a particular frequency that you want. So you're honing on to a particular frequency, resonant frequency or your Larmor frequency here. So that your resonant coils that you have, you're tuning it to the Larmor frequency. So you know omega naught is 1 by square root of LC. So of course you have a coil, you have to have some safety limit because the heat could be generated, and so it's usually done to keep the temperature rise less than a degree. Okay. So types of coils, so you can have different types of coils. What do we mean by that? Apart from transmit receive, I said, what do we mean by different type here is, you can have a big coil, right? You can have a big coil which can have which we call homogeneous field. So you have it for the whole body, whole head, everything, any location can be done. So this is a whole body coil. You can have dedicated coils also, bird cage, saddle, right? Here you can have surface coil. So you can have surface for knee, you can have elbow, you can actually have a dedicated receive only coil for a particular location. Okay. So you have different coils for different objects, different parts of the body. Of course, all of them should operate within this range. Remember this range. What is this range? We are talking about 42 megahertz is your Tesla. So you should be able to operate. Gradients are going to change it over a range. But remember our limits. Mostly we are talking about 1.5 Tesla, 3 Tesla kind of scanners. So this range is in some sense operatable for biomedical imaging. So different coils, just demonstrative. We are not going to spend too much time on this. So you can have a bird cage coil. So essentially you are putting your tuning circuit. You have some construction like this. So that it's called as a bird cage. The shape and the sketch gives you the name as to why it is bird cage coil. Okay. Of course, here you notice this is B1 is in the X direction. So always notice where do you want your body is Z direction, right? So you are always going to. So we talked about Z axis. Your measuring always is going to be perpendicular, transverse component. So if your Z is like this, your measuring is going to be perpendicular to that, right? That is how this is. Okay. So like that you can have surface coil. Notice again B is here. Your surface coil is measuring the XY component, right? The XY direction. So you can have dedicated coil like this. It's not a big deal. Coils are nothing but loops which have some tuned values. Your frequency, it is tuned for a particular resonant frequency. Okay, so you can have several different coils dedicated for different organs, like you see here. Breast coil, head coil, wrist coil, right? Torso coil. So you see the size and shape is changing depending on, of course, several of them, these are for small animal. Okay, we have mice or something, you can, this chamber is also small. So you have a surface coil. So these are very core electrical. If you are interested in electrical circuits, antenna, those kind of area in electrical, I think this will be very interesting and very important area that you can contribute. For the purposes of this course, we have just understood what is the physics. We know the role of this, and we know there are capabilities, how this is going to affect our image and image quality. But we are not really interested in circuit design, because that is not our goal of this kind of course, which is introductory on imaging system. So we will leave it here. Whoever is interested has a background, you may have to jump in. But this is a very interesting and active area there where you can contribute. Okay, so we'll stop here because next we need to move forward. The instrumentation is the three major components we have covered. Okay, now we need to go on to see how we use all these instruments or these components. We understood physics, so how do we use this to realize the data and organize the data so that we can go to image formation. Okay, image formation, and once we know image formation, here we'll talk about essentially how you are collecting the data, and then how do we represent it as a reconstructed image. Okay, so those are the two topics that will be covered in the next two lecture videos. For now, for instrumentation, I think we'll stop here. Okay, thank you.